to talk about material and energy balances in reactor design. Consider this lecture as an extended introduction to reactor design. And here I am going to talk about the general understanding of material and energy balances. I will deal with the details much later in other lectures, but as of now, we are going to talk only about the general idea. So, for the starting point of any design in chemical engineering, we have to obey the law of conservation of a particular factor, either law of conservation of mass or energy or momentum. Okay, so starting for material balance is the point where you take into consideration the law of conservation of mass. Now, to elaborate on this, I'm going to take an element of the volume of the reactor. What do I mean by this element of the volume of a reactor? So let me just consider this reactor vessel. Okay, where my drawing skills. This is a reactor vessel. Okay, you have some reaction going on over here. Now, one thing I have explained in the first part of the introduction, that is, depending on the position and time of the reactor volume, the composition can vary. Okay, so there is a space coordinate and there is a time coordinate working within this reactor volume. Now, if throughout the reactor the composition remains uniform, then you do not have to worry. But that is not guaranteed in a real world application. So, I am only going to consider a small chunk of this entire reactor volume. Okay, that is what I will be considering for my material and energy balance in general. So, let me take this differential element. So this differential element is a small section of our actual reactor. Okay. So on one point, the reactant, let me say A, enters, and at one point the reactant A leaves the reactor. And within this element, or within this small reactor volume, the reactant A may accumulate, or it may, you know uh, I shouldn't actually relate this accumulation in this manner. Let me put it in another way. So let's say you have this reactant being consumed by the reactant, or there may be some generation of some new product, but considering only the reactant, we'll talk about the consumption or disappearance of A. And another thing that we say is accumulation of A. So some part of the reactant may not have reacted, but is still inside the reactor vessel. So that we are referring to as accumulation. Now, if I put up the law of conservation of mass and I carry out the material balance, then I will say the accumulation is equivalent to the input minus the output minus consumption. So all of these are with respect to A, that is your reactant, right? So this in general characterizes the material balance. Now, if the like I said, if the composition within the reactor is uniform, that is, it is dependent of this space coordinate, then you can account for the whole reactor. But if it is not uniform, then you have to use this differential element of the volume, and this has to be integrated across the entire reactor. Okay, of course, while you're integrating, you have to obey the appropriate flow and concentration conditions. We will get into the details of this, but as a general idea, the first step is always to study the material balance. Now, for depending on the reactant type, reactor type. So we know the reactor types are batch, semi-batch, and steady state flow reactors. So depending on type of reactor, this general equation gets simplified. So in case of a batch reactor, you do not have any input or output term. So input equals to 0 and output equals to 0. Okay. If you have a semi-batch reactor, then you have the output term equals to 0. But if you have the steady state flow reactor, then the fourth term, that is the accumulation, or like I should say the left hand side term. If I consider these three to be the main governing terms, then this becomes my fourth term, the left hand side term of accumulation. This accumulation disappears because everything is moving out of the system, it's a flowing system. So accumulation becomes 0. But for a semi batch reactor, where some kind of output is being taken out, okay, there are semi batch reactions where periodically output is taken out. It's not like a flow reactor. Okay, in my first part of this introduction video, I have showed you the picturization of a semi batch reactor as a circular reactor where A is already present and you are adding B as per the requirement. But sometimes it happens to help with the progress of the reaction, some amount of the product is also taken out, and this happens periodically. It's not continuous like in a steady state flow. So in that case, this output may or may not be 0. So output is 0 if you have no outlet, but if you have an outlet, then all of these terms need to be considered. Okay, so considering a very simple semi-batch reactor, I would like to say that the output term is 0 because we are not having any outlet at all. We are having periodic inputs. Okay, another thing that we need to think about when we refer to reactor design is whether our reaction is exothermic or endothermic. So, is there a temperature difference? Okay, and accordingly whether any cooling measure is required or if any heating measure is required, so this must be taken into consideration when we talk about reactor design. This is where the energy balance comes into play. So now we'll talk about the energy balance. Now this is generally when you have a non isothermal operation. So isothermal means temperature remains constant. In that case you can only work with the material balance. But when you have a non-isothermal operation, that is, your temperature is varying, you must consider energy balance equation. So energy balance equation is again same. How do we do it? So accumulation of heat within the system. Uh, Instead of writing system, I'm going to write that reactor element of reactor volume. Reactor volume equals to input minus output, uh, minus, I should write minus over here, minus heat consumption by the reaction plus heat generation by the reaction. So depending on whether your system is exothermic or endothermic, these two last two terms will vary on your right hand side. Okay, so if you are having an endothermic kind of reaction, then obviously heat will be consumed. But if you have an exothermic type of reaction, then your heat will be generated by the system. So these two are like the main building blocks of reactor design. And to study any real world system, the idea is that you incorporate this material balance and energy balance together. Okay, and this is done by using their generation or consumption terms. Okay, now these, like I said, they form the starting point of all design aspects in reactor design. And uh, if you are considering the differential volume or the element of the entire reactor volume, then obviously you have to consider their integration, okay, across the entire reactor. When we'll be able to predict the response of the reacting system to the changes in operating conditions like rates or equilibrium conversion with respect to temperature, pressure, and when we are able to compare the yield means how much of the product output you are getting, okay, or the desired product output that you get, that defines the yield. So once you're able to compare the yield for different designs, okay, then you can proceed for the economic study of your reactor design. And once that economic study is done, then we can arrive at a conclusion that yes, now the design is ready for the process at hand, and we can like go for a real time operation. But arriving at this stage where you are ready with a design involves a lot of sub steps, and the first starting point is the energy balance and material balance. So that is it for the general discussion on reactor design. In the next lecture, what I plan is to like get you acquainted with the different symbols and relationships which are prevalent when we study with reactor designs. So till then, thank you.